All right, so here's an example. It's probably not similar to a problem that I would ask on an exam, just to let you know. I picked a problem. I thought, ooh, this sounds like a good problem. And then I posted it, and then I wanted to retract it because I didn't quite like it. But too late. Posted, must be done. So we have, and I want to calculate the damping and stiffness coefficients for an accelerometer in this figure right here. Whoops, come back to me. And with a moving mass of 0.04 kilograms, such that the accelerometer is able to measure a vibration between 0 and somewhere in between there. Let's see. FF is somewhere between 0 and 50 hertz. And it says within, and so this is the tricky part, within 5% error. Now, what they're essentially going to do is they're going to actually design it for 0 error or pretty darn close. So I don't, this is the part of, for me that I went like, when I went to work on this, and I tried to solve it, I was getting frustrated, and then I looked at the solution, and I get kind of angry at them. Like, you kind of cheated here, but that's okay. Cheating's fine. So they are within 0 error, but they're using something that they already know. And the thing that they already know is that it's nice to stick within R is equal to 0.2 and squiggle is equal to 0.7. Knowing those two things, you can make your accelerometer. You can design your accelerometer. So it's kind of like aggravating that you had to already know this. So starting out with those two known things, we can already find out the natural frequency, and we can find the stiffness because we're given the mass. We're given the mass, so we know that R is going to be equal to omega F over omega N. So let's just go ahead and find omega F at the extreme of 50 is just going to be 2 pi F, right? So that ends up being a value. Or I could have done it in another way. I don't know why I didn't do it this way first, but that's how I did it right there. Okay, so I've already committed to it. So I guess you guys don't really care, do you? Well, it's going to be 100 times pi, right? So it's going to be 2 times f, which is 50, times pi, and you can do this in your head, but still you're writing it down in your calculator. 314.2, right, radians per second. So omega n is going to be omega f divided by r. I do that right? I hope so. So that's going to be 314.2 divided by 0.2. We already discussed where that, that 0.2 is a really important like range. Like let's set that there. We already set that that 0.7. So it seems a little hinky to me that the rest of the stuff that we're about to do, and it kind of seems a little pointless. We go 1,571 is the natural frequency of the accelerometer. And using the fact, let's change colors because colors make things better. Omega n, natural frequency is the square root of k over m. So we can find what k is going to be equal to by multiplying m by the natural frequency squared. That we get these 0.04 and times 1,571 squared. And that ends up being 98,696 newtons per meter. Now, the bogus part of this is just we're kind of using this next equation for the sake of using this equation. So I don't mean to get like testy about the thing, but it is a little annoying. We want to go the error, right? So the 5% error, which we're going to ditch. We're going to totally ditch this in a second, which is going to be, we're going to say that our accelerometer term is going to be 0.9, is going to be somewhere between 0.9 and and 1 over square root of r, well, I did, again, that 1 minus r squared, whole thing squared, plus 2 squiggle r, that's squared, right there, 1.05. Right, we want to find a value. So we already have r. We already picked out r. Now we're going to see what squiggle will produce these two results. And so sticking in the 0.2 into here and distributing that square root thing to both sides of this, we end up finding 0.8317 plus 0.1444 times squiggle, and we have 1 in the middle, and then have 1.016 plus 0.1764 squiggle. Oops, sorry, squiggle is supposed to be squared. And based on this, I didn't even bother to calculate out what the squiggle had to be, right? All we end up finding is that, and I guess I don't know why I didn't copy it. I'm not going to. I didn't write it down, or I didn't calculate it out. But notably, squiggle equals to 0.7 satisfies this. I know. I was angry too. Satisfies this. Therefore, use squiggle equals 0.7. What a letdown. So now we can find the damping. We didn't even have to do this. We just double checked that it fit inside there. That's just obnoxious. We could have figured out the error. Oh, might as well. We could have just plugged that 0.7 in there and figured out what the error was and saw that it was less than 5%. It would have been satisfied. But no, had to do this. So let's see. We're going to say that C is going to be equal to squiggle times CC, which is squiggle times 2m omega n squared. So we end up with 0.7 times 2 times the mass, which is 0.04 times natural frequency 1,571 squared. So we have a C equal to 87.98 Newton seconds per meter. And I feel like I got ripped off, because what the heck? I also didn't rewrite out my K. I should rewrite these things at the end, but my K is going to be 98,700. No reason to go any more than 3 sig figs in these solutions right here. So let's just make this at 88. Use the correct color, like anybody cares. All right, so there you go. There's the solution to this example. I'm going to see if the next one is nearly as ridiculous as this one. We'll see. Come back for more.